Hi. So as Paris said, we both work on a research team within Cisco that is um, primarily our day job is we're building an assistant, AI assistant, sort of like Siri or Alexa. But we're building it for kind of the business world. So you can imagine when you're having meetings or whatever, you might talk to it and make calls with it, things like that. But something that's come up when we're doing our work is that all these AI agents, you right now just can talk to them. So you have to every time you want to talk to them, you have to wake them up. Alexa, blah blah blah. And that's not how humans do it, right? If I was having a conversation and then before every sentence I had to say, Dario, let's start the presentation. Dario, are you ready? You would become repetitive and it would seem really stupid. And so, we have these devices that have really good cameras and microarrays. So we have high quality input coming in. And so we thought, well, let's take advantage of this high quality data to be able to understand what a person is doing more naturally. And so what we're going to show you today are a series of demos where we're basically trying to do that, to make more natural interactions. You have a question?
Yeah, on the keyword, don't they use the keyword partly to then start recording? So Google only actually start recording you once you say, hey Google.
Right.
Isn't that part of privacy as well?
It can be, but so when I'm talking to you, you're aware of that I'm addressing you when I do things like look at you or gesture toward you. So if I'm like talking quietly to Dario here, you know that I'm not addressing you. But if I turn to you and start, doing this, suddenly you know I am. And so partly what we're going to show is how you intelligently know that you are being addressed without waking it up.
Yeah, so one of the key ideas was to look at how our brains work. We have an amazing machine that works with just a few watts of energy and does really amazing stuff. And if you look how it evolved, we see different parts of the brains. We have the old part of the brain that is encoding the inputs, which is actually shared with other animals like reptiles and birds. And they're very good at one task. The whole part of the brain that is connected to my eye is very good at encoding properly my vision, hearing, and different senses. Then we have this newly evolved part, more recent, that is common in all mammals, which is the neocortex. And it seems like the bigger it is, the smarter we are. What this does is a common algorithm that gets all these different inputs encoded in a common way and does a high-level reasoning just by using this very same algorithm. And we see that it's very flexible because there have been some experiments, very interesting experiments, where you can rewire in mice the nerves from the ears back to the vision part of the neocortex, and then eventually mouse learns to hear with the part of the brain that used to see. So this flexibility, this adaptation of this simple algorithm that is just repeated and repeated over and over again with billions of neurons inspire what we want to show you.
And so partly this is inspiration for how we architected what we're going to show you. But also, if you look at the little graphic there on the left with the blind woman holding the device, what's happening there is it's the camera in her glasses is turning the incoming signal into a set of electrical activations on her tongue. So there's a little sensor on her tongue that's pricking her tongue in particular patterns. And our brains are able over time to repurpose parts of the neocortex to reinterpret information in a new way. So she's actually able to see by feeling the vibrations on her tongue. And you might think, well, how could you process it that fast? You can't consciously, but our brains over time rewire themselves to be able to interpret new information using a different part of the brain. And so she's basically learning to see this way. We also have heard about experiments where they're teaching deaf people to hear by turning sound into a set of vibrations that can be played on a haptic device. And we're actually going to show you in a little bit how to kind of what that feels like. We have one here that does some of that. So, but the main takeaway here is that we thought, well, let's create an AI that does something like this. So it's going to have all these different inputs, sight, sound, what else? Touch,
yeah,
possibly, any motion
yeah.
detection. And it's going to take all these inputs and it's going to receive them and it's going to encode them just like the brain does into a common vocabulary that our neocortex can process. And so our main neocortex is just going to have to be able to understand a single way of encoding information, and it's going to be able to learn from it.
Yeah, this is, so we mentioned the structure, the architecture of the idea. So we have multiple senses, and then we have the main brain, the neocortex. It's this loop, this program that is always running in a loop and waiting for information from the senses. That's why we made this loop. So you can picture it like in the center, this program running and running and waiting for information from the ears, from the microphones, from the cameras, from higher level reasoning, other higher level senses, motions and everything. And you can see all these multiple loops communicating with each other. And this is sort of, we took inspiration also from other works from other authors. And this idea of a loop within a loop where intelligence arises, because you create higher level of reasoning the more loops is stuck together. So probably it's very abstract as a concept, just picture like this, but you can just picture something always listening for events, my neocortex, and events as in senses. I hear a sound, I see a face, must be real. And then that's how we build reasoning, by simply stacking simple senses.
Right, so the idea basically is that from a lot of simple things, if you put them together, you get complexity. If you were looking like down a darkened alleyway and you see someone that you think you might know, but you're not sure, but then you watch them walk a little bit and their gait seems familiar, and maybe you hear a bit of their voice and it sounds like your friend, and so your brain is able to put all these signals together kind of effortlessly and identify it as your friend, and you're not even really aware this is happening. And so that's kind of the same principle we're trying to mimic.
So now we'll show how we build little by little something that gets smarter and smarter. So we talked about senses, and we want to start from the very easy ones. And like babies, we start from what's the simplest thing that a baby can do? And it's just recognizing when something happens. So when mom is talking or not talking, very simple binary. It's the first way to get attention from a cat. A dog is making noise, and then that noise can trigger it. So you can see the red dot is a feedback for you guys. When they don't talk, nothing happens. But when they talk, the red dot appears. It's very basic sense. Nothing complex. Anyone can do it. It's a voice activity detection. But we want to show how we can build something very complex, something very smart, by just doing reasoning on simple events, simple senses.
And you can imagine if you've got a child or a student, you're trying to teach them something, the first thing that they might need to be aware of is someone talking, right? Because that means that something interesting might be occurring. So that's why we started with that. Okay, so something very simple.
Yeah, the second one is something that babies can do it yet. They need to be probably 3-4 years, no, probably 2 years old or something.
I think it's like 3.
3 or something, which is object permanence. It's easy for a machine to say, okay, this is a hand, and then I move it, and then a machine just says, I see a hand, a hand, a hand, a hand. But saying this is the same object through time is not that simple. It's very simple for us. We do it seamlessly. We don't think about it, but it's a skill we gain when we are 2 or something years old. And computers have a hard time doing that. If I show a hand and I hide it and I show it again, oh, new hand. No, it's the same. So something we built. Let's build this simple sense we do easily, and then let's build reasoning on top of that. Now we can show just.
Yeah, we can show what that looks like. But babies love playing peekaboo.
Oh, yeah.
It's partly because, for them, it's a new person. It's like you disappeared from the universe and suddenly you're back. They're back again. And they're constantly surprised by this.
Yeah.
But if I played peekaboo with you, you'd be really bored. Because you're like, well, you just put your hands in front of your face, right? But babies can't figure that out yet. And so most object detection algorithms can't either. What they do is they say at every frame of the camera, they're like, cat, 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 cat. But knowing that it's the same cat is not something they do natively. So we'll show you what that looks like. So right now I'm just going to tell it to track faces. So it's going to just track me and Dario. But it can track any object. In fact, we can even show it random objects and it can follow those, even if it's never seen them before. So you can see that it knows it's me, right? And I can try to fool it, if it's going to find me. I can go off the camera. It's like I lost you. But when I come back, it's the same color, meaning it still thinks it's the same person. Now, it doesn't know who it is yet, but it knows there's a face. So if Dario comes into the picture, it'll pick up his face. And so it knows there's two of us, but it doesn't really know, who we are. Dario goes away. It'll lose him for a second, but if he comes back, hopefully it gets him again. So it's able to track him across time, both of us, and know that we're the same person. Yeah.
Is that based on the color of the pixel? Or do you guys do like a store the
It's not pixel driven. So the way it works is that these models are trained on thousands, millions of faces, and they learn a way of describing faces that captures the semantics of a face. It's not the particular pixels, it's features that it learns about faces. Oh, we have lots of hands.
I think what you're saying is facial recognition, then it identifies those as an object on that, and you don't interact it.
No, that's just the center of the face. It's
So it doesn't detect as a nose, as an object, but it just picks up the center of the face.
Yeah, in this case, it's just the little track you're seeing is just the center of the square. It's not tracking my nose.
It just happens to be in the center.
Yeah.
Yeah.
Sorry. How about you? Sorry, in the middle, the lady. No. So you give it lots of examples of what faces look like, and it learns whatever it learns. So it learns a vector, a set of numbers, which those numbers are weights in a machine learning model that it just learns represent a face. And its only objective basically is given the same set of numbers, it should recognize that to be a face. Sure, I mean, there are patterns it's recognizing, but it's not like they're scrutable. You can't, it's not like somewhere you see that it looks for eyes and noses. And the model may not care about those at all. It probably does, but it's hard to say exactly what the numbers mean. Did you have a comment?
If you just put something on the nose, like it's still gonna detect as a face and the center point of face. That's how it works.
Say that one more time?
What it does is basically it detects as a face, like an object.
Yeah.
And then 3 points in the middle of the head, that's where it wants.
Yeah, I mean, all the line is to indicate that it is the same object. So it's just like a trail is all that's trying to express. We could, I can show it this water bottle and it would follow the water bottle. It doesn't matter what the object is. What it's doing is it's learning a way of representing any object in a way that it can follow it. Yeah. Yes?
What's the key factors or criteria in telling the difference from different objects? How can I tell it's A and B? What's the key factor?
Do you know?
Yeah. So as we mentioned, they're kind of unscrutable. What deep learning models do, these neural networks, what they do, as if you ask me, say, what does make the camera different from that camera, right? You can say, okay, that's more to the left, it's more gray, it's a bigger, input, or I forget, 2 cables, whatever. I can express it. When we want to describe things with these deep learning models, they learn all these features and they describe it with numbers. And what we do, we just compare the numbers they provide to us. And when these numbers are are similar, okay, these are the same vector. These are the same objects. So my face through time is described with numbers that are similar to each other, that are though different from the numbers that Will's face produce for these models. And the same with a bottle. Would be a Coke bottle would be different from a Sprite bottle because it's green maybe, but I can see it's green. Maybe a deep learning model sees other features. It's just difficult to describe what I see. There are studies on that.
You can think of what they learn as a point in space. So imagine you had a bunch of photographs of people on a table, and some of those photographs were the same person, and you can visually look at the photographs, and you can push pictures that are of the same person kind of into a little pile, and maybe even pictures that look something like that person get close to it. So the model sort of does something like that, where it's trying to put objects that are close to each other semantically or visually or whatever, close to each other in this higher dimensional space. So rather than having 3 dimensions, you might have 300 or 1,000, but they're really just points in space. And so Dario might be here, another picture of Dario might be here, Will might be over here. And so when you get a new face, it plots it, sort of, and we say, okay, what face is that nearby in that higher dimensional space?
This is, I don't know if you're familiar with the net things. It's ResNet 18, which is 18 layers. It's not that deep. We have thousands nowadays. But we use different models for different senses. So now the next one is going to be another sense. We have different weights, different models, whatever works. What we want is encoding different inputs, sound, voice, movements, whatever, in the same representation that the main loop can process. It was a
Yeah, so can you push it to the point where the algo will be able to determine ethnicity? And if you can reach that point, can you push even further where you'll be able to teach the robots how to identify basic genetic traits for that specific person as him coming from the northern Africa or sub-Saharan Africa or something like that.
So it basically learns what you want it to learn. That's yeah. That is also the difficulty of you might want it to learn something and learn something else. So maybe there are many things to know. Training these models is not that easy, right? So you see, if your objective is to identify certain differentiate in a certain way, you can force it to do it. So this model was trying to differentiate between faces to say, okay, this looks like the same person. But yeah, you can do different things. We can actually talk about what we did with voice. For speaker recognition, we did something similar, but with the way I talk. You heard me talking for what, 10 minutes now, and you can already differentiate my voice from his voice. It's instantaneous for you because you have a smart way to represent the way I talk, my accent, my pitch, the way I pause, the way I pronounce this word, the way I pronounce this other word. You put everything together and say, okay, this is Dario. And then, someone else comes, John comes, Will comes, and say, okay, this sounds like John, Will, and whoever. Because you put together all this information. Yeah, we're showing this now is three way of presenting my voice. One is the usual one on top, the waveform, the amplitude of the compression in the air, simple. The second one is the spectrogram, which is just showing the frequencies that my voice is producing through time. So you can see high, low frequencies, and mainly machine learning models use this representation. It's easier. It's like an image. And then these dots, that's my voice, as we were saying, in space. And this model is trained to compress it to a 300-dimensional vector, a sequence of numbers, so that my voice will always be in a certain area in this higher dimensional space. Now we are just compressing in 2 dimensions because we don't see it otherwise. And if Will starts talking now.
Yeah, so it's been hearing Dario's voice, so it's been trying to vectorize or turn Dario's voice into a set of numbers. But now it's beginning to hear mine, and you can kind of tell that it's beginning to kind of create another cluster over here on I don't know if it's your left or my right, but you can see there is beginning to be a separation between the 2 blobs of dots. And so what it's basically doing is it's learning to represent my voice in a way that lets you separate it from Dario's. So we're teaching the system basically, even if you don't know whose voice it is, you can learn that there are 2 people, or that person A is talking versus person B. Okay, so that's another kind of fundamental thing, right? Is mom talking to me or is dad, right?
It's very similar to what we with faces, but now with the voice, with the way I talk. And you can see just drawing a line and say, okay, you can then afterwards saying that was that was Will, and then boom, you have a speaker recognition. We don't have no. We do one at a time. Yeah, works on the double talk, double. Well, that's just a representation. It's the vectors are actually 300 dimensions. So it's I don't know how to picture it. I'm just compressing down to 2 dimensions. So it doesn't really matter. That's how I represent my voice with a sequence like 1, 7, 3, 4, 7. It's 4 numbers, 5. That's 5 dimensions. That's a vector. So it doesn't really. If you talk at the same time, it's a totally different job trying to separate the voices. It's not done this way.
Yeah, right. The model you saw running there requires about a 3-second window of speech to vectorize that segment of speech. Yeah. So in order to really like people talking over each other, or they're like in a fast-moving play or something, you have to bring that down to like, I don't know, 50 milliseconds or a second or whatever it is that would be necessary. It's definitely possible. I mean, humans do it all the time, right? So it's really just a technical hurdle. I think it's possible to do that.
We have a trick for doing that, and we're going to show it. So
yeah, we sort of cheat.
We use what we have, so you'll see in a couple of slides.
Yeah, I mean, I won't say too much, but we do what humans do. Okay. All right, so before we get to that, another way that humans interact with each other is through gestures, right? Like we point, we do this, we wave at people. And so we thought, well, okay, one way that an AI might learn to interact with you is just by you sort of doing those things. So if I say hi, you know that I'm addressing you. So we built a system that can recognize gestures. I'll show you what that looks like. Now, what you're going to see here is a representation of space and time. So you're seeing me as I move through time, right? And the reason why we represent the view like this is it helps the system know what to pay attention to. So rather than caring about like the color of my shirt or the background or whatever, it's sort of laser focused on motion. And so we're just helping the deep learning model kind of do its task a little easier. But I can like gesture at it, and it knows that I waved at it, right? Hi. Or I may be like, go away, or go that way, or number one, or good job, right? So and the way we taught it this was we literally, it's seeing the world this way, and I literally did this, and I said, okay, that's a wave, and I did it again, I'm like, that's another wave, and I did over here, and that's another wave, right? And so we literally just have people doing gestures like that, and the system learns to represent it. And we can even do this in real time. So the system can learn new gestures without like some big offline training task. It is possible to do online learning. So you're like, okay, system, I'm about to teach you what it looks like to do like a swirl or something. And then you kind of do the little swirl. Right? So it thinks that's kind of a wave still probably. But we can tell it what it is, and it can learn a new thing. And so you can imagine not just that you can interact with gestures, but that you can teach it new ones.
Yeah, so one thing we want to point out is that we sometimes rely on end-to-end deep learning models where features are extracted from raw data, like in the audio that you saw before. Sometimes also we want to be smart, we want to help it, depending on the task. So for the gestures, we want it to be to help it a bit, saying, don't look at it, as you said, the color of my shirt. What you care is what happens through time. So that's why we worked on this kind of compression of information. This led us also to have, as you said, training in real time instead of having to provide thousands of pictures or videos of wheel waving, because it has to learn what matters and what doesn't matter. So it's a combination of different techniques, different ideas that led us to build something that can build something complex, more and more complex.
Yeah, and we think it's techniques like this that allow the brain to operate on such little energy with such a limited capacity, because it doesn't try to always solve the hard problem. Like when you are, say, catching a baseball, in calculus or in physics, you might do some kind of complicated 3D calculus equation to figure out how to where the ball is going to be, where do you put your glove to catch it. The brain doesn't actually do that. It turns the 3D space into a 2D representation, and it just says, I see a little thing here, and it's a big thing here, and it just creates a little parabola between those 2 points in 2D space. And so it's little optimizations like that. If you're a biology major, maybe I'm not. Maybe that's not true, but I think that's true. But it's optimizations like that the brain takes advantage of. And we often are running these models on really low-powered devices because we want them to run on the edge, as they say, on the devices out there in the world. And this one's running on my laptop, right? There's no GPU or anything in this. This is all CPU-driven. And so by giving it a limited input, we're able to let it work faster. So, bye-bye.
Yeah, so next I think we have, gaze detection. Something you mentioned, yes, before, when you say, okay, Google, it's for privacy, you want to know exactly when you interacted with it. The way we do it as humans is very naturally. I can look at you, I'm talking to you. I'm looking at you. It's simple. Interaction is simple. I know I'm talking to Will now. So being able to do this seamlessly and very efficiently is also another step towards building something that is able to pay attention to you or to whoever, whenever it matters. It's a simple task, and since we have cameras, why not using it? Now I think Google and Amazon came out with the ones with cameras and screens. I'm not sure they have also cameras. They have screens for sure. They're trying to build more on top of those. Cameras also scare people for privacy reasons, of course. That's also one reason why we want to build everything locally. Everything is running locally on a CPU, on laptops. So what Will is showing here is so the green cube is, when it's green, it says, okay, you're looking at me. When it goes gray or when it disappears, it says, okay, you're not looking at me. That's a very simple way to detect it. And also, there are multiple people. Now it sees me, but I'm not looking at it. If I look straight to the camera, it says, okay, you're looking at me.
Yeah, so you can imagine, and we'll show this later, if you're doing this, it sort of doesn't think I'm talking to it. But if I look at it, now it's like, oh, Will must be about to yell at me, right? So, this is another signal we use to know when it should interact. Yeah.
Do they do this by combination of the sensor that you use, so either camera and laser, or do you distinguish? Do you combine those two data sets to recognize whether you're not looking at the device, or mainly looking at the visual?
Yeah, this is all visual, just using the webcam in my laptop. There's no other hardware here. The way that this works is that it first trains on landmark detection, so you can see the little dots on my face there. If I get closer, you can see it more clearly. And those correspond to like my mouth and nose and eyes and such. And then those landmarks are fed into another algorithm that's detecting whether you're looking at it. And so we basically said, okay, we give it examples of what looking at it and not looking at it are, and it learns to figure that out. Right.
So, next one is the trick for knowing when people are talking to, who is talking, for example. So the idea is, again, inspired by humans or other animals. We have multiple microphones. We have 2 microphones. And with that, I can recognize where the sound is coming from, right? Very simply. Usually, we have microphone arrays in multiple devices at Cisco, but also the Alexa has multiple microphones. That's how it knows where you're talking, where the sound is coming from. So now we're going to show you an advancement of what we showed before. It's not just sound detection, but it's sound localization. The same dot as before as a feedback, but we have multiple ears. In this case, we have actually 6 microphones. And with a simple algorithm, we can detect where the sound comes from. So now it's coming from the right side for me, and it appears on this side. If Will talks,
if I talk, it should jump over to my side. So it's actually tracking in real time where the voice is coming from. And if I walk and talk, it should actually come with me, blah, 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 testing, 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 blah, 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 blah. Right? And you can think of this as like
testing,
an eye,
testing,
like looking around. Yeah, so before we just said that the dumb, like someone's talking, now it's like not only talking, but it knows where the voice is coming from.
And directing in the right direction.
And you can imagine how you could combine, something like the speaker vectorization earlier that we did with this to figure out who's talking, right? So the sound's coming from the same spot, so it's probably coming from the same voice. And so you can very quickly switch back between people and not mix up their encodings.
Yeah, sounds like Will, but it looks from different position. It's not Will. Maybe the other person sounds like Will. Simple reasoning on those.
This would be a linear distance between microphone and source. So it sees everything in terms of 2D, not 3D.
In this case, it's a 2D plane. We have 6 microphones in a circular, if we cannot lift it. It's a circular microphone array, so 6 microphones. So the same input comes, and we just calculate the distance, the difference in time between the same input coming, and we just do the triangulation of the source.
Right, but you could do a more sort of 3D triangulation. Yeah. You were talking about that today. If you had 2 of these microarrays on different planes, then you could do 3D localization. Yeah.
I forgot what's.
Let's look.
Oh, attention.
Right.
Yeah, so we can focus on what matters with sound, but also we have eyes, and we are very sensitive to movement, for example. If I stare at a blank wall, nothing interesting happens. If something moves, I turn and look, oh, something's happening. So what we wanted to build is a sense that is gonna look into what really matters in the scene. So the camera is looking at the frames through time and differentiating between the current frames and the previous frames and saying, oh, this is different, so I'm gonna look at it. That's also how I get attention to my cat. It's like, oh, look at it, I wave. And also that's what we do when I see something that changes through time. If I see someone entering the door, even if I'm not looking, my peripheral vision can see it. I don't see very clearly. I see probably blurry and black and white because my vision is blurrier and black and white to the sides. I see it and then turn and I can focus on it. So what we have here is something that they just described. He sees movement and he focuses on that. And you can see also there's some delay on it. So it's like the persistence we have with our retinas. If I look at something for long enough and I move, I still have the image in my brain. That's how we think we see in full HD, but we actually don't. We actually see full HD just in the center. And then we just keep the image, we build a puzzle every second, sort of.
Yeah, your vision actually, like Dario's saying, has a little tiny focal point that's really clear, and your brain is always moving your eye around, and it's capturing this very high-res version, and it kind of puts all those individual moments together, and your brain stitches it into a single image. So when you look at the world, it feels to you like it's a big clear image. In reality, it's not. It's a bunch of fuzzy images with a little tiny clear image, and they're all stuck together in a way that makes it seem like the world is focused. But what you can see here is like as I move, like it's going to pay attention to me, and it might jump over to Dario if he like does something. So it's trying to figure out what should I pay attention to. And if we look at the kind of like the kind of debug view of this, this is just purely based on movement, and so you can see the little dots following me around, and you can see that it's paying attention to me right now. But
moving a lot.
Sorry. But Dario can grab its attention, or I can say, look up here, right? And see the dot is paying attention to my hand now. So you might, I might say, hey, this is Dario, and it, pays attention to who I'm pointing at. But we can add like other signals to this. So let's say we want to add the speaker tracking signal that we had earlier. So we want to make this a little more complex. So now we're going to have both motion and sound detection. And you see the red one's the speaker tracking, and the blue one is the motion. And right now, because I'm talking and moving, they're both paying attention to me. But if I stay really still and keep talking, and Dario starts moving, but not talking, you'll see the red's still on me, but the blue's on him. So it can pay attention to two things at once, just like we can. But if I start moving again now, I've taken control.
Yeah, so this is what we do. We see something moving, we we visually see something that is interesting, and also we pay attention to it. We see where the sound comes from. Also, this creates some robustness on what to pay attention to. Even if I'm deaf, I can still see things. I can pay attention to different things that are important. Or a sense goes wild or doesn't work properly. This creates redundancy and robustness on the decision we want to make. So now it pays attention to me because I'm both moving and I'm talking, and it's pretty sure it's me, the important person to pay attention to.
Okay. Okay, next is
Oh yeah, reinforcement learning. I don't know how many of you are familiar with reinforcement learning. I try to give a 30 seconds understanding. So we have, this AI revolution is using mainly supervised learning, which is you give an input to this neural network. You say, this is a picture of a cat. And it says, it's a dog. Wrong. And then it adapts. The more pictures of a cat or a dog we show, the better it becomes. This is supervised learning. For each input, we provide the right answer. Then it is the unsupervised learning, which is the very same, but we don't say what each input is. It just had to, the AI needs to figure out something out of this data and say, okay, this looks similar to each other. It's a very complex matter. We don't give the right answers. Reinforcement learning is something that we felt is the more natural way to teach to machines. It's also the way we teach dogs or to pets or to humans. We just we let it act for a sequence of, for a certain period of time. For example, when you teach a dog to sit, what the dog does is performs a sequence of actions. It needs to decide, okay, I'm going to sit, which is bending my knees and staying down. And it's a sequence of decisions. And only at the end we provide, that was good. We just say, good, we give a treat or not. That's the idea behind reinforcement learning. We let the AI perform a sequence of actions, and at the end, only at the end, we say, that was good, that was bad. And the idea is that it's eager for good feedbacks. And we don't have treats, but it's positive numbers. Like a +1 is a treat, and a -1 is a bad. It's like not a spank. Maybe it's a no. It's called reinforcement learning from the psychology for training pets. And so is it to your left? Yeah, to your left, we have the usual loop. We have the environment, which is what happens in the world. It's sounds, people moving, waves, and everything. And we see that, we hear it, and that's transferred to the agent. Agent is the AI, what we're building, as a state. What's happening now? And also we provide rewards. The environment says, okay, that was good, that was bad. And the agent then interact with the environment with actions, saying, for example, is deciding where to put the focus. So if I hear the sound from here and I see movement here, then I need to decide where do I want to put my focus. And the rewards can be, for example, I want to teach it to follow my face. And whenever the focus is close to my face, I provide a good feedback. We also want to, I put myself, me, on the right side, to have explicit rewards. If you want to teach it something more complex, we can interact with it more randomly. And when the agent decides to do something, when happens to do something good, I can give a stronger reward, saying like +10. And then eventually we'll learn, okay, it did something very good. For example, it got my attention when it was important, or it reminded me of something very important at the right time. These are actions that it will take. And probably you want to talk about experiment you did with the buzzing.
All right, yeah. So we actually tried to make a dog, kind of, and we wanted the dog to sort of like you have like a golden retriever or something, and you don't want it to bother you too much, but sometimes you want it to come up and you want to pet it. And so we wanted to create an AI through reinforcement learning that could know when to bug us and when to get our attention. And so the way we did it was we gave it some senses or abilities. We let it beep at us and buzz us using these haptic devices, which I guess we should show that now, shouldn't we?
Yeah.
Right, I should have done this before. I'll keep talking for a second. But we gave it abilities, right? And we said, okay, now figure out how to get our attention. And we would reward it by basically paying attention to it, looking at it, talking to it. And when we didn't like what it was doing, we would ignore it like you would kind of a noisy dog, right? Or you might yell at it or whatever. And so in about 20 or 30 minutes, the system learned a fairly sophisticated policy. And what it would do is it would kind of like buzz us a little bit. And if we didn't kind of respond, it would leave us alone for a little bit. And then maybe in a little bit, it might kind of nudge us again and buzz us. And then we'd be like, okay, we'd look at it, good boy. And it learned to kind of like be patient, but when we gave it a lot of attention to keep asking for more as long as we'd let it. So it was able to do this through reinforcement learning. What we're going to try to show now is this is a haptic device with some vibration motors on it, and they're like a grid. And what we're going to do is we're going to encode our voices into one of these encodings like we showed with the little dots on the map, and we're going to play it on this device. And this is sort of how the AI was talking to us. And we're going to just pass that around here. Let's first pair it up.
We sort of wanted to give, instead of giving a voice, the way we like actual, when we talk to Alexa or Google, it talks to us the way we hear the human way. Wanted to give it a more complex way of talking to us. And we'll mention this experiment where deaf people will learn to hear with these haptic devices, with these vibrations. Then you start making sense out of these vibrations. And you're going to feel it. So now, when I'm talking, I'm encoding my voice into 20 different into these 20 different motors.
You can pass it around.
Yeah, I can pass it around. I can open it up and put it on your arm. I can hear me talking. And if you wait long enough.
So Dario, can you fill it on? Is it buzzing now?
Yeah,
Okay, so it's picking up my voice in the microphone. It's running it through our deep learning model, creating an encoding of my voice, and it's playing what I'm saying on that device. Now, to you, it probably just feels like a bunch of noise, but you can immediately tell when I'm talking, right? So if I stop, it stops. So the first thing you can tell is that something's happening. But our brains actually, in a fairly small amount of time, can learn to turn those vibrations into actually understanding what's being said. And we did an experiment where we took incoming text messages, and we encoded those using this method, played them on our wristbands. We actually had a full vest too, for more, kind of precision. And we were able to, after about a day or two, at least know who it was from and maybe kind of some of the words they were saying, right? So, you can imagine instead of getting like a notification on your phone, and you get the same notification whether it's your mom and your house is on fire, or it's like, a spam, right? So this might be a way of differentiating the content of the notification. Is it something important or not? And your brain can actually very quickly learn to feel what is important, which is pretty amazing. So we can leave that running as we're running the experiment here. But okay, let's. Okay, well, that's what we were just talking about.
Exactly. The next thing is. So we can see the word, we know what to pay attention to, we can have this conversation between humans and machines. We have all this complex behavior. But what really matters is to be able to remember things. I mean, it's not very important is to remember, after all this learning, we want to remember what matters, right? So we want to build a memory. It's like, the example you made to me. If you go to the same coffee shop every day, and you say your name the first time and the second time, they keep asking the same person your name, you say, this guy is not that smart. Or if you always for espresso, you go there and say, so the usual. So it learns what, you want to remember things properly. You want to create a representation of memories of what you see, of what you hear, what I tell, and then be able to recollect it when it matters, and associate it to each person in a personal way. So whatever is important to Will, we need to remember it, and what is important to me, we need to remember. So you can explain.
Yeah. So we essentially gave it a way to remember things, and similar to the way that we can vectorize faces and voices, we can do the same thing to text and information. So we can encode text semantically, in terms of its meaning, and represent it as a set of numbers in this higher dimensional space. And then use the exact same technique we did with faces and voices to figure out what sentences are like each other. So I'm going to show you how we teach the thing. So here's a couple of sentences.
I think we lost the connection. This Bluetooth
It's
connection.
probably too far away.
Yeah, sorry for that.
I'll go ahead and stop it. So so I'm going to teach you a couple of things. The barn is red, and the cat ran across the street. And so what it just did there was it learned that information, and it represented it in space. And so these two dots are actually points in space. And if I zoom in on one of those, it's just a sentence, and you can see the parts of the sentence here. And so right now their relationship is based on the distance between them. But it's learned a couple of things. So the barn is red. So we can ask it a question like, what color is the barn? And it's able to tell us that it's red. We can say, which animal walked down the lane? Now, what we taught it was the cat ran across the street. But we're going to ask it, which animal walked down the lane? Totally different text. But it's able to tell us that the cat ran down the street. And if we look at the actual, some of the things it thought were interesting, it thought cat was a kind of animal with a kind of 0.4 probability, and it thought streets were probably like lanes. And so it learns that concepts are like each other, and it's able to realize that certain sentences are like others. So you can think of this as like a semantic search, search based on meaning. But let's teach it something harder. Let's give it here's a few paragraphs off the Wikipedia article for Berlin. And I'll clear out its memory. So now it's totally dumb again, doesn't know anything. I'll paste that in. Now it's learned all of those pieces of information. And the colors represent, it's trying to figure out which ones belong together topic-wise. But really the distance between the dots is what's important. And again, each one of these is a sentence, right? Or some sort of fact that it's learned. So we can ask it some questions now, like, what's the largest city in Germany? And it tells us that's Berlin. But we can ask it something harder, like, what was the capital of the Weimar Republic in 1920? And it tells us that, what is it? Berlin is the answer. And so there's some things to note here, like we said 1920, but it says, well, 1919 is close to that. And so it's able to answer the question even though it didn't explicitly find the very question asked. And it's all because of this sort of fuzzy semantic distance, right? Yep. Yep. That's the grammar of a sentence is what you're seeing there. Yeah. And it's hard to see with these complicated sentences, but we have one neural network that's trained to understand grammar, and so kind of the first thing it does is it gets the sentence and it says, here's what I think the grammar is. And I remember in high school having to do this manually, and drawing the lines, and so luckily we don't have to do that anymore. These algorithms are actually better than humans at doing this now.
Sorry.
How does the machine respond in case they don't know the information? What was the answer?
So because this is based on really a distance in space, if you ask it a question that is far away from anything else, we literally take and say that distance is too far from any nearby thought to be related to it. And so you can threshold it based on that distance.
Yeah, probably the thing is, you can see it can learn from unstructured text. It's not something we don't pre-process thoughts or phrases or anything. We just give it the way we would say it. The sentences on Wikipedia are the way we talk. But we are able to learn something that we can represent in a formal way by just by using these neural networks. I learn to compress unstructured text and formalize it so that even we can do math. That's how computers reason. We can do math on sentences, on phrases, on thoughts. So that's your question.
it's cosine similarity is the measurement. It's just basic math. You have 2 points, and they happen to be in 1,000 dimensions or whatever, but it's the same principle as if they're in 2. And you literally just say, how far is that? I mean, it's pretty amazing that meaning can be encapsulated that way, but it can be.
So you can use this to kind of make like a fact database sort of thing, but like how do you try to get answers when you search questions? Some of those questions when you Google them, like the answers in variables, is that because of the native version, like the spaces, the distances are incorrect?
It's more because these models still don't understand the way we do. And so even what I just showed you, they have the appearance of understanding, but they really don't. They don't know what Germany is. They don't understand dates, not really. They're just ways of representing text as numbers and doing some math. But so the sort of beyond the state of the art in machine learning right now is to understand things like logical reasoning and negation. And like if I said, don't show me pictures of cats, you're probably, if you type that into Google, going to get a bunch of pictures of cats, right? That's like an obvious thing humans would never fall for, but something simple like negation like that is easy to fool a computer with, and that's the simplest of them, right? If you said, show me things which are cats but not dogs, and that go to school, and that also, if you start getting more complicated, they get worse and worse. So what you're seeing a lot of that is just the limitations of what we can do.
Also the fact we combine different experiences. So if you say the word dog, I have an experience, a visual experience, I have memories of interacting with the dog, I have a deep understanding of what concepts are. These things are, for the memory idea is mainly just compressing sentences. So there's not much more than just compressing the semantic and the grammar together. So if you want to build some complex reasoning out, smart search engine with Google, probably you need to encapsulate more information, more senses, more memories for each thought or possible query you might have. Even probably, I don't know what technology you're using, but if you say Dr. Brown or Brown Doctor, they are the same thing sometimes in this hyperspace because the order sometimes doesn't matter that much. But Dr. Brown is totally different from a Brown Doctor. So it can be multiple things.
Okay, so we're just about done here, but what we're going to show you now is trying to take all of these senses and put them all together and have the AI do something smart. So we're going to, I won't tell you what's going to happen, but we'll see what happens. But so we're going to be running like 7 or 8 different models on this laptop. So if it takes off and flies across the room, that's why. Okay.
Yeah, we have a bunch of script to run, so it might take a few seconds.
Yeah, so the first thing I'm going to do is start up basic face detection.
No lens? Show lens.
No, I'm not showing it.
Okay.
Oh, I didn't want to do lens, right? Just that, right?
Yep.
Okay, so the first sense is just that there are some faces going on here. And then I'm going to add speaker tracking that we showed earlier.
So again, the main loop is running. So the neocortex is running, and now we are plugging in senses.
Right, and so you should begin to put a couple things together. So now it's getting a sense of that there's a voice. So we're going to keep making it smarter. We're going to add motion tracking to this. So now it's be able to hear voices, follow them, and see the face. And then we're going to give it the ability to talk to us. Let's see here. Okay, so now it can talk to us. And we're going to let it understand what we say to it. Okay, so there's a lot going on here right now. Okay, so right now it's trying to figure out what to pay attention to. It sees a person, it's listening to me, and already it's smarter than most AIs because right now it's listening. And if Alexa were listening to me right now, I'd be saying, "I've never heard of that. What are you talking about? I don't understand that." And so I'm just going to look at it and start talking to it, and it should be interacting with me. We'll see. Who am I?
I'm not sure yet.
My name is Will.
Hi, Will.
Okay, you can see it's labeled my face now. And I can leave, and it can ignore Will, but now I'm still Will, right? So it's learned my face already. And so I'll ask it some questions because I haven't taught it anything yet. What's my favorite color? What's my favorite color?
I'm not sure about that.
Remember that my favorite color is blue.
Okay, I'll remember that.
Okay, and so I taught it something. Now I can later, I've got to forgotten what the answer is, so I'm going to ask it again. What's my favorite color?
Your favorite color is blue.
Ta-da. Now Dario, if he comes in, it's not going to tell him. That's good about my color.
What is my favorite color?
I don't know.
Doesn't know. If I come back in, what's my favorite color?
I don't know.
Oh, yes you do. What is my favorite color? What is my favorite color?
Your favorite color is blue.
See, I told you I knew it. Okay, so now Dario can teach it something.
First, my name. My name is Dario. My name is Dario.
Hi, Dario.
Yeah. Remember that I left the keys on the table.
Okay, I'll remember that.
So maybe tomorrow I can come back and where are my keys? So it's tomorrow. Where are my keys?
You left the keys on the table.
Thank you.
Yeah, so we're kind of showing how you can put together a lot of things to, each one of them is sort of dumb, but when you put them together, they do something which starts to look a little smarter. And right now it's listening to me, but it doesn't know anything about what I'm saying, so it just is ignoring me. Okay. That's it. So we'll take questions now.
Yeah, we can.
Are you able to ask? I don't know what's your name.
What's it?
The name of the program.
Doesn't have a name. We try not
didn't
to
give
give
it a
one.
name yet.
Are you able to ask the program what Will's favorite color is?
We can.
Yes,
we can. We don't. I mean, for now, for the demo itself, we don't. We have two different brains, or n different brains. As many people we introduce it, but we could. I mean, you mentioned privacy before, one of you. So we can have different brains that are not totally separate.
Yeah, what you're seeing here, this is Will's brain, and this is Dario's brain, and we can actually, it learned this when we were just talking to it, and so it learned. Okay, I left my keys on the table as Dario's thing that it learned, and for me it learned, my favorite color is blue. But we played around with this thing where we basically can let other people know certain facts if you let them, right? So I can say, let Dario know that, and so if Dario asks, then he can know it. But it's an explicit.
Yeah.
I give it permission to do that.
How about ethics? How the algorithm is able to comprehend the meaningfulness of ethics and what is ethical or unethical across states, regions, countries, and cultures. You think, because right now that's the primary question I have in mind after what you just saw, right? What is your program on that? Do you have any efforts into that, Cisco?
We've thought a lot about this question.
Yeah.
So our backgrounds are kind of weird. Dario was a professional violinist originally, and I was a philosopher. So we have a weird background. We think a little bit differently about these things, and we care a lot about that question. And just right now, AI is seen as somewhat scary, I think, by a lot of people. It's tracking people, it's giving them jaywalking tickets and weird things like that. And so we're very interested in building AIs that do care about you. And one of the ways you do that is you teach them, just like you would a child or a dog, how to behave. And coming up with like a school for AIs is pretty critical, or else we'll end up with like a million Microsoft Haze, which I don't know if you remember that, but they put it out in the wild and let it learn from Twitter, and it got really nasty really quick. So we do need to think from the very beginning, how do you train something that is sort of smart so that it doesn't do anything terrible and cares about us. Sorry.
Oh, sorry.
I think you.
What if you have twins on front of the camera?
So we actually did this. Our friend has 2 twin kids, and it could tell them apart.
Yeah.
So it's actually better than we are at that.
There are subtleties that are invisible for the machine. Yeah.
Mm-hmm.
So it recognizes the 3 and 4D, right? So if you put like a picture of like a face, does it say that it's a face or not?
Yeah, we could show it a video. It would follow the video face. Is that what you mean?
Yeah.
It recognizes as a face, basically. So it would like point it like face on the screen, even if it's only a picture.
Yeah, we don't have a 3D understanding for now.
It does, but there are ways of.
Yeah, we have.
Usually people that do things like LiDAR, things like that to do depth. Or if you have 2 cameras, you can do depth and make sure that it's a real face. But I think how about you? Yeah, I mean it can. So you can point it at any data source. Like you can give it a book. I gave it Alice in Wonderland the other day, and it was able to read it. And then I asked it, what happens when she drinks the potion? And it said she got smaller or whatever it was. So yeah, it can just go read is one way to do it. But you can also, we have ways of building like adapters that if you have some weird data source, you can just teach it how that data source works, and it can go.
Connect your cell phone or you connect another like division, you could extract all the information, so you can start like learning more.
I mean, you could. I assume that's possible, but I mean, this is not. I mean, I don't want to overstate how smart this thing is, right? It's not like there's no danger of it like right now looking at all your phones and crawling your phones.
Yeah.
But it could if that were.
One moment cannot like what type of movies do you like or what type of books do you like. And you can say like, well, my favorite color is blue, but you're going to say no, my favorite color is yellow.
Yeah, you could give it your Netflix preference list or your Facebook likes or whatever, and it could learn a lot about you that way.
Yeah, all the pictures you liked, all the pictures you took. You like mountains, clearly. There's no limit to what you might learn. Sometimes he learns without you knowing it. It makes, there's something also that happens many times is you provide certain inputs, certain answers, and then expect that it learns something, but indeed it learns something else. There's a story in the Second World War. I think it was the Russians. They trained dogs to hide under tanks, and they would wrap them with explosives so that during the war they could make German tanks explode. And then they did it and it was successful. And then they tested it in during the war, and the dogs would actually run and hide under Russian tanks instead of German tanks because they didn't learn to hide under tanks, but they just smelled the exhaust, and the exhaust smelled different between Russian tanks and German tanks, and they didn't. The test worked, but then in real life it didn't work. So they learned something else. And we call it a dog sometimes because we learned something we didn't expect.
Right.
How did it take you guys? How did you product your development? And like, why did you guys actually say this product maybe being something that you would give to your customers?
I mean,
How long? 6 months more or less.
yeah, it's not far away from being part of things we're working on. Some of these features are already making their way into our devices. But a lot of this is just experimentation. We're not really sure what will end up being useful. we're just trying to figure out, given we can do all these things with machine learning, which ones will actually make it more seamless to interact with AI.
Maybe a follow-up question to that. You also have like a vision of how you see the end product, the hardware aspects of it, as in will it be like a center piece on a table with a 360 degree camera, with multi-directional microphones and everything, or will it be one touchscreen TV with a camera and a row of microphones in it and stuff? How do you envision that?
We don't want to limit ourselves for now. So we envision a few things. One he described is very, very close to what we thought. 360 camera, 360 microphone, and it's an object that you care eventually because it cares about you back. But it can also be the HAL 9000 probably one day. So we don't want to limit what this can become. But totally we like, also one reason why we're working on running everything locally is that privacy, do I trust this thing, where is my information going, oh my god, he's watching me. But if instead it's not connected to the internet, and it's on your table, and if you destroy it, it's gone, that's also an idea.
And we also want to, we want this thing to have superhuman senses, right? So we're not just trying to recreate what we can do, but, imagine if you had 1,000 eyes, and you had perfect hearing, and you had other senses like electromagnetic or LiDAR that you don't have now. How would you interact with the world? So we want to build it in such a way that we abstract the particular senses, and we just say, okay, you might just be able to see. You might be able to do 15 different things. It doesn't matter. You should be able to learn, interact, no matter what senses you have coming in, just like if I happen to lose my sight tonight, hopefully not, tomorrow I can still get around by using other senses or maybe replacing it in some way.
I had a comment interval on the frequencies of sentences. What did you use to structure the weights of the comments?
It's kind of complicated. It does a kind of first pass that's sort of more like traditional search, which uses like term frequency and versus document frequency kinds of calculations. And then it does the semantic cosine similarity, and that gives it another probability. Like two sentences are very, very similar, are going to be very, very close, and so forth. And then it puts those two sets together, and it does a final score, which is, I don't know how to describe it, but if you think of two words that appeared in the original sentence, if you think of them being on two ends of a rubber band, you then look in the final sentence that you're scoring, and you say, how far did I have to stretch those apart to find them in the candidate sentence, and how similar were they, right? So it's not just exact text, but it's, if you have two words that are kind of like each other, you just have to stretch them even further. And so you get this kind of, how far did I have to distort the candidate sentence to make it like the original one? It's up here. We wrote most of these.
Yeah.
We do use standard frameworks like TensorFlow and PyTorch and stuff to train our models, but most of the stuff is not. It's not like you just can grab something off the shelf. But okay, I think that's it. So thank you.
Thank you.